Hi guys, today we're going to be talking about type theory, what it is, where it comes from, how it works, and what it's used for, how it's going to be used in computer science, in linguistics, in logic, and in philosophy. I think this is going to be a pretty big one, so grab your cup of tea, strap yourself in, here we go. So type theory is, like the name says, a theory of types. So to understand it, we need to know what we mean by types. And the best way to get a grip on that is through some really simple examples. So here's a really simple example from basic arithmetic. Let's talk about the natural numbers. Call that nat. That's going to be the type we're interested in this example. Okay, so 0, 1, 2, they are all objects of type nat. Okay, now think of the kind of functions that we can do on those objects. So we've got the successor function or the +1 function. So that's a function that takes in one natural number and it gives us back a natural number. So it's got the type nat to nat. Okay, we're going to write it like this to mean it's a function whose input is a natural number and its output is a natural number. Okay, pretty simple there. We've also got the addition function. Okay, what's its type going to be? Well, that takes in two natural numbers or a pair of natural numbers and spits out another natural number. So we can say it's got this type from a pair of natural numbers, we'll write that like that, to a natural number. But there's another way of thinking about it, okay? Rather than thinking of it as taking in two natural numbers at once or a pair of natural numbers, we can think of it as first taking in one natural number and returning another function from a natural number to a natural number. Okay, often when we do type theory, we're going to consider functions like this. So this is sometimes called the curried form of that function. It always takes in one input, but it gives us back another function, which maybe takes in one input and gives us back another function until we get the output. We should call this a function from natural numbers to functions from natural numbers to natural numbers, but let's just abbreviate that to it's a function from natural numbers to natural numbers to natural numbers. And it basically means the same as from a pair of natural numbers to a natural number. Okay, so there's some simple examples of some types of numbers and types of functions from basic arithmetic. Here's an example from linguistics. So here we're going to consider two basic types. We've got the type of individuals, so like people, let's say, we'll call that I, and we've got the truth values, because in linguistics, ultimately we want to evaluate sentences for their truth. That's kind of how we're going to assign meanings to them. So we've got the type T of truth values. So in a linguistics context, we can either assign the types to the words or to the things that they denote. In the semantics, we can kind of do it either way. Let's just do it with the words here. So we've got this name, Anna, that's going to denote an individual. And then we've got this verb, sings. Okay, so that is going to be something that takes in a name for an individual and gives us back a truth value depending on whether that person sings or not. Okay, so it's going to be of type I to T, from individuals to truth values. So one place predicates like sings are going to have type I to T. Okay, a transitive verb, a two-place predicate like likes, okay, X likes Y, that's going to be something that takes in two individuals and gives us back a truth value depending on whether the first person likes the second person or not. Or the way we're going to do it here, we're going to do the curried version. It's going to take in one individual and give us back another function from individuals to truth values. Okay, so it's going to be of type individual to truth value. Okay, so given that those words have those types, we can start combining those words into meaningful sentences. Okay, so likes needs an individual term first, like Anna. So likes Anna, that is going to be something that takes an individual term to a truth value. Okay, so likes Anna combined with Beck, that's going to be something of type T. A sentence, something that has a truth value. Let's just continue this example a little bit further because it gets a bit more interesting. Okay, so we've got sings of type individual to truth value. What about a quantifier like everyone? Well, forget how quantifiers work in logic for the moment. Just think about how they work in English. We would normally say something like everyone sings. Okay, so everyone should be something that takes a predicate, a one-place predicate, to a truth value. So everyone is going to be of type I to T, that's predicate type, to truth values. So its input is going to be a predicate, the output's going to be a truth value, so we can form everyone sings. That's going to be a sentence of type T. It's going to be true or false. Okay, great. What if we want to get a bit more complex here? Rather than just everyone sings, we want to say something like everyone likes Anna. This is going to be a bit more tricky because given the types that we've assigned so far, the only way of putting together everyone likes an Anna is like this. First of all, we have to put Anna together with likes to give us something of type I to T. That is going to be the input to everyone, so we can form everyone likes Anna of type T. However, this isn't going to be the sentence that we wanted, everyone likes Anna. Likes Anna is going to be a predicate applying to the people that Anna likes. Okay, so if likes XY means that X likes Y, then likes Anna means Anna likes whoever you apply to that function. So likes Anna means Anna is doing the liking, so everyone likes Anna means Anna likes everyone. But that's not what we wanted to say. If we wanted to say everyone likes Anna, that's not something we can yet do. To be able to do that, we are going to need lambdas. We're going to need to use the Lambda Calculus. Type theory and Lambda Calculus, they go together so well that they're basically considered the same theory in computer science. We're going to get onto that in a bit. If you're enjoying the video so far, do me a favour, give it a thumbs up, subscribe to the channel, that really helps me out. And if you want to help support the channel, you can buy me a coffee over on Ko-Fi or sign up there as a channel supporter. Okay, before we get to the details, let's talk a little bit about where type theory comes from. It's got a really interesting theory. Let's go right back to the beginning because type theory, like lots of stuff in philosophy and logic, it starts with Frege and Russell. So Frege, he was interested in trying to understand all of mathematics in terms of logic. Okay, he wanted to reduce mathematics to logic. That's a view known as logicism. He had this principle he called Basic Law 5, that every concept has an extension. In modern terms, we might say that every predicate or every open sentence determines a set of things, the things that satisfy that predicate. And this principle was central to Frege's demonstration of the reduction of mathematics to logic. Unfortunately, the principle is inconsistent. This is what Bertrand Russell noticed. And one way of seeing that it's inconsistent is with the Russell set. Okay, so we think of sets of things that contain themselves, we think of sets of things that don't contain themselves, and then we try to form the set of all sets that don't contain themselves. Okay, then ask yourself the question, does that set, the Russell set, contain itself or not? Well, if it does contain itself, then it's by definition not a member of itself, contradiction. And if it doesn't contain itself, then by definition it does contain itself. So either way, we've got a contradiction. It's a paradox. It's Russell's paradox. It's a paradox of naive set theory. Okay, this confused a lot of people at the time. Not just philosophers, but logicians, mathematicians. They thought there might be a problem right at the heart of mathematics, and a lot of people tried to work out a way of formalizing logic and mathematics that wouldn't have this kind of problem. And the solution that Russell came up with is type theory. So he developed this in an article, Mathematical Logic as Based on the Theory of Types, 1908, and then this forms a central part of his Principia Mathematica, this kind of huge book, or 3 books that he published with Whitehead between 1910 and 1913. It's a bit tricky to see exactly what Russell's type theory looks like because although it's the central part of Principia Mathematica, which is this huge formal work of logicism, he doesn't really spell out the type theory in perfectly precise formal terms. And basically it's a very, very complicated theory because he wanted it to do many, many things. It's not what we call simple type theory, it's called ramified type theory. He wanted his theory not just to avoid his own Russell's paradox, but also to avoid any kind of circularity in definitions, what are sometimes called impredicative definitions. And basically as a result, the theory got kind of really hairy and complicated, and yeah, it's just not very nice. We're going to make life a little bit easier. We're going to look at simple type theory. Russell's theory really didn't catch on at the time. Partly because it was so complicated, but also because around the same time people have been developing new kinds of set theory. So you've got Ernst and Milo, 1908, so same time as Russell's theory of types, and that was kind of added to later by Frankel. So you've got ZF set theory, Milo-Frankel set theory. You've also got Thoras Skolem in the picture there. ZF set theory kind of doesn't do everything mathematicians want set theory to do, because it doesn't decide the axiom of choice. It doesn't prove the axiom of choice, but it also doesn't prove the negation of the axiom. So what are you going to do? A lot of people just add choice as a basic axiom, and that gives you ZFC set theory. And that's been super successful as a foundation for mathematics. It's used by working mathematicians like all the time. You open up a book on mathematics, there's going to be some set theory in there. You know, you're probably not going to see type theory. So Russell was kind of unlucky, I guess, in that a competitor theory did really well, and that meant that type theory was almost forgotten about. Quote here from Skolem, 1922, Russell and Whitehead too constructed a system of logic that provides a foundation for set theory. If I am not mistaken, however, mathematicians have taken but little interest in it. Yeah, that was definitely true for many years after Russell developed type theory, but then things started to change. And one of the reasons things could change is the development of the Lambda Calculus. Lambda Calculus was developed in the 30s by Alonzo Church. I'm going to give you a super quick overview of it here. I'm going to skip out loads of details, otherwise we're going to be here all day. Okay, let's start off with the pure Lambda Calculus without types, untyped Lambda Calculus. What have we got? We have got variables, they all count as terms. We've got constants, they all count as terms. Okay, and if you give me any two terms, one thing I can do is put them together. That's called an application. That's a term. And the other thing I can do is I can abstract on that term. So you give me a term, I can form the lambda abstract. Basically, I put lambda x or lambda y, any variable, in front of it, and that counts as a term. And it's this kind of construction, the abstractions, that really is the interest in Lambda Calculus. What does it mean? Well, good question, but think of this as creating a function from a term. So I'm kind of adding an extra argument place. So think of this as a function, and that is its argument. And what we're doing with an application is I'm taking a function here and I'm applying it to this term here. So creating a function and applying a function. So we can think of the abstractions as function definitions, and we can think of the applications as functional application. So the terms of Lambda Calculus, they're really terms for naming functions. Okay, things get a bit more interesting when we add types. There we've got the simply typed Lambda Calculus. Okay, so to do a system of types, I need some base types. So that might just be nat, or it might be I and t for individuals and truth values, whatever. Got some base types, and then we have a recursive definition. So one way to do simple types is to say, whenever I've got two types, I can put an arrow between them. So alpha to beta is going to be a type. Sometimes you'll see this written like this without the arrow, or there's different ways of writing it, but basically we're always saying it's a type from type alpha to type beta, and we're going to think of things of that type as basically being functions from alpha type things to beta type things. Okay, so if those are the types, what does the simply typed Lambda Calculus look like? Well, its terms are going to be, we're going to have variables of each type. We're going to have constants of each type. If I've got some term m of type beta, and I take a variable x of type alpha, then I can abstract. Okay, so lambda x of type alpha m, that's going to have type from alpha to beta. Okay, because the variable has type alpha and m has type beta. Think of this as a function from alpha type things to beta type things, and we can do applications. when m's got type alpha to beta and n has type alpha. Okay, so an application kind of works when the input has type alpha and the function, that's m, has type alpha to beta. So that term should have type beta. That's the output type of a function when the input is type alpha. Now I'm kind of running a few things together here. I'm giving you the definition of the terms, that is the syntax of the language, and I'm telling you what types they're going to have, okay? Often in a computer science setting or a proof theory setting, what we're going to do is we're going to first define these things, our language, and then we're going to set up a proof system with a bunch of rules that take us through proving these things do or don't have a certain type. Okay, we're going to look at that in a bit. Now that we've got our lambdas, let's go back to the problem that we had before, our linguistics example, where we're trying to say everyone likes Anna, but the only way we could do it is like this, and that's going to mean Anna likes everyone. That's assuming that likes XY means that X likes Y. What we need to find a way of doing is putting these words together kind of in a different order, applying them in a different order without breaking these types. Here's how we can do it. So likes needs two individual inputs. So we can take an individual variable X and a name Anna. That's going to make a sentence, something of type T. And then we can abstract on that X. So we get a lambda abstraction. Lambda X likes X Anna. Okay, this is something of type from I to T. So it's a predicate. Think of it as a function from individuals to truth values. And we're abstracting on the first place of the likes relation, okay? That's the person who does the liking. So the person who will go in for X here is somebody who likes Anna. That is, if they like Anna, the value is going to be true. And if they don't like Anna, the value would be false. So what we've got here is a predicate, meaning is a person that likes Anna. And it's the right type to be the input to everyone, because everyone wants a one-place predicate. So we can form the sentence, everyone, lambda X, X likes Anna. That's going to be of type T. It's going to take a truth value, and it's going to mean that everyone is an X that likes Anna. Everyone likes Anna. That's what we wanted to express. And we can do that because we've now got access to lambdas. In effect, what we've done is we've taken the lambdas and they've allowed us to swap around the argument places of likes so that the first thing you put in isn't the liker, but is the person who is being liked. Okay, that's the kind of thing you can do with lambdas. Okay, so there is a super quick introduction to type theory, but what is it for? How does it get used in various different disciplines? Computer science, philosophy, linguistics, and so on. Let's start with computer science. So in this setting, what we're often trying to do is prove that a certain term has a certain type, or to put it another way, that a certain type is inhabited. There is some term that belongs to that particular type. Okay, so the way we would prove that is kind of like in a proof system. So we're going to have a bunch of rules, a bunch of axioms, and what we're going to try and prove is that term T has type alpha. Let me give you a super simple example of how that might look. Suppose we just take it as axiomatic that our constant 0 is a natural number. Okay, so it's got type nat, and the successor function has type nat to nat. Okay, takes a natural number to a natural number. One kind of inference rule that we've got is the application inference rule that says from those two things, I can infer that this term, successor applied to 0, is of type nat. That's pretty obvious, right? If a function takes me from nat to nat and I give it an input that's a nat, the output, successor of 0, is going to be a nat as well. Okay, nothing particularly exciting going on there, but as often in proof theory, you combine a bunch of super simple things and you get interesting things. So we can do it again. We can apply that same structure to our successor function again, and we get the successor of 0, i.e. 2, that's a natural number 2. We can do the same kind of thing with our addition function. So if we take it as an axiom that that's got type nat to nat to nat, then we can combine that axiom with our previous proofs to infer first that this term is a predicate from natural numbers to natural numbers, and this term is a natural number. Okay, so adding 2 to 1, that's a natural number. So one thing to notice here when we are doing proofs involving types, that is a kind of type checking, we're not actually calculating the numbers, right? We're not calculating the answer of 2 plus 1. What we're doing is we're saying, what kind of type does that expression have? It's going to be a natural number. We're not saying what natural number it is. We're just saying it's got the right type. So when we're doing program verification, type checking in a formal setting, like with computer programs or whatever, we're not always checking that the program is going to give us the right answer. We're checking it's going to give us the right kind or the right type of answer. Like it's not going to give us something completely random. It's not going to throw an exception or try and put the wrong kind of thing into the next bit of the program where it kind of gives up and goes home. Okay. That's kind of what we're doing when we're type checking program verification in computer science. Okay, let's take this idea a little bit further. So we've shown the highly exciting results that adding the number 1 to the number 2 gives us a natural number. But what about if we wanted to do something more general, like adding any 2 natural numbers gives us a natural number? How would we do that? So what we're going to do is make some assumptions. These are called contexts. Our proofs are going to be proofs from assumptions or within a context. Okay, so our assumption is going to be that we've got 2 variables, x and y, and they are both standing for natural numbers. So our context is going to be this, x and y are natural numbers. And our proofs are going to be proofs from that context. So we've got our axiom, we've got x is natural, y is a natural number, and we can reason as before and say that x added to y is a natural number. So we could take this further with some universal introduction rules because x and y are basically dummy variables. And we could infer that adding any 2 natural numbers, x and y, will give you a natural number. Okay, now let's have a look at how type theory works in logic. And this is going to be related to higher order logic. So what do we mean by higher order logic? Well, lots of people are familiar with first order logic. The first order bit there means that our quantifiers are quantifying over things. The x in fx, okay, so over people and rocks and chairs, objects basically, particulars. Then we've got second order logic. Here we've got quantifiers that quantify over the predicate position. So you can think of that as meaning quantifying over the properties and relations. Okay, so this sentence might mean for any property, if A's got that property, then B's got that property too. Okay, you don't have to read it in terms of properties, but it's kind of what's going on in second order logic. We've moved up a level from the objects to the properties of the objects or the ways that they are. Okay, go up another level, we're now talking about third order logic and we're talking about properties of properties. So things like red is a colour. Okay, I'm applying a property being a colour to a property being red. Red is a colour. So a sentence like this, here we've got a third order quantifier. This is a property of properties. So what this is saying is there is some property of properties, like, I don't know, being a good property, such that for any property, if it's one of those, like if it's a good property, then A and B don't differ. So this might reflect a situation where A and B share all their good properties, but maybe they differ in their bad properties or, something like that. So here we've got some specific levels of logic. First order, second order, third order. Type theory gives us a way of going up the orders or up the type hierarchy, up as high as we want to go. Okay, so arbitrarily high. Kind of what we've been doing implicitly in these logics is saying, here's a predicate and it's taking an individual variable, and here's a quantifier and it's quantifying over individual variables, and here's a second order quantifier, it wants a second order variable, and here's a third order quantifier. So we're kind of defining these implicitly with types by saying what kind of thing does it want as input and what kind of thing does it want as output. So if we do that in a completely general way, we use type theory, and then we can have logics of any type or any order. Okay, to make that a bit more concrete, a bit more specific, let me give you an example of one particular higher order logic. So this is from Gallin, 1975. It's called TY2. Okay, so to define it, first of all, we define the types. So we're going to have 3 base types. We've got E for individuals. We've got S for, in effect, possible worlds or world-time pairs. Kind of ignore that for the time being. And we've got T, the truth values, like we had before. And the complex types of the theory are just the ones that we saw before. So you give me 2 types, alpha and beta, and I can put them together in a new type. So we're just writing this to mean the type from alpha to beta. Sometimes we write it without the arrow, basically just to save space on paper. So that's the types. What do the terms of the logic look like? Well, we've got constants of each type, variables of each type. We've got lambda abstractions, and we've got applications, just like in the simply typed Lambda Calculus. We're also going to be able to form a term A is identical to B whenever we've got 2 terms that are the same type. Okay, so we've got identities not just between objects, like I am the person talking on this video right now, but also between like properties. So saying that, being triangular is the same as being trilateral. So we've got the ability to form identities for any type. Okay, that's quite a novelty of higher order logic. We've also got a special type, things that are of type T, like the sentences. They are the formulas, and we are going to apply logical operations to them. So negation, conjunction, disjunction, and universal quantification. In more complex type theories or higher order logics, we might be allowed to apply some or all of these operations to things of any type. So like if you say, me and you, that is a conjunction applying to individual terms. We're not doing that here. We're only applying the logical operators to sentences, just like we do in standard logic. That kind of keeps everything a little bit simpler. Okay, what does all this stuff mean? Well, we give this logic a semantics, and the way we do that is through frames, okay? Frames is just a way of assigning the terms of the logic to basically functions. So a frame is a set of sets. We're going to have one set D alpha for each type alpha. Really, these can be anything we want as long as those 2 aren't empty, and the domain of the truth values has to be the truth values, so 0 and 1, or true and false, or whatever you want to call them. And then for each complex type, alpha, beta, we want that to be a set of functions from domain alpha to domain beta. So we're interpreting the terms of a complex type from alpha to beta as functions from the domain of alpha to the domain of beta. So the domains kind of run in lockstep with the definition of the types. And then on top of this, we give a truth definition, which tells us when these sentences are going to be true or not. So we inherit all the stuff we know and love from standard logic. So for instance, a conjunction, it's true. It's just the minimum of A and B. So it's true when both A and B are true, and it's false otherwise. But we also have to give denotations to the other terms, the lambda abstracts and the applications. Applications are easy, right? Because if we're applying A to B, A's got to be a function, and B is going to be an argument that we can put into that function. The type system guarantees that. So how do we interpret A applied to B? Well, we just apply function A to input B. Easy. So what is the denotation of a lambda abstract going to be? Well, we want it to be a function. We want this to be a function that takes in things of type and gives us back something in the domain of the type of whatever A is, okay? So this is going to be the function such that if you put in any D from the domain of A, it's going to give you the denotation of A. Okay, that is quite a mouthful, but if you work your way through that definition, it's basically just saying it's the function it should be. It's the function from things of type alpha, such that you put in any one of those things in, and it's going to give you back the denotation, the meaning of A relative to that input. I am being a little bit sloppy here because A might have some free variables in it, in which case we have to substitute into it. But, rather than going into the whole business of variable assignments and that, let's just leave it as, it's the function that we kind of expect it to be when we do a lambda abstraction. Okay, so this is not the only way to do higher order logics. There are loads of different varieties, but this gives a sense of how we can come up with a very well-defined logic using type theory. Let's move on to linguistics and how type theory gets used in linguistics. Now, this is a huge subject because if you look at any textbooks on Montague semantics or formal semantics, compositional linguistics or whatever, it's basically going to be just chock full of lambdas and type theory. In some ways, modern compositional semantics just is applying type theory and possible world semantics to natural language. Okay, so these theories are kind of so closely intertwined. Let me just give you a few examples here just as a flavour. So suppose we're trying to understand adjectives, okay, like quickly, okay, so I can run quickly or I can run slowly or badly or whatever. So quickly, how does that function as a term? So let's think about how quickly might work, what its meaning might be. It's not really working like our property of a property example that we had earlier, right? So red is a colour, okay, I'm applying the property is a colour to a property is red. But I can't really say, runs quickly. That doesn't make a sentence. It's not true or false. So it's not a property of a property. Really what it's doing is it's taking a predicate and it's transforming it into a new predicate. Okay, so taking a predicate like runs, which is something I can do, and it's transforming it into a new predicate, runs quickly, which is something I might do or not do. Okay, this is called a predicate functor. It's something that takes one predicate and gives us back a new predicate. So it's got this type, okay? It's taking in a predicate, something from individuals to truth values, and it's giving me as output something from individuals to truth values. So the input might be runs and the output might be runs quickly, okay? Something that applies to me is false, but applies to a speedy person is true. So then we can analyze a more complex sentence like runs quickly and gracefully, not something I do, like this. So here we've got one predicate functor, an adjective. Here we've got another. And we've got this dummy variable here. We can lambda abstract on it. And that gives us a one-place predicate, something from individuals to truth values. And it's going to apply to people who run quickly and gracefully. Okay, so we've got a predicate formed from these predicate functors. And a nice thing here we can do is we can use the deductive power of type theory, of type lambda calculus to beta reduce. Okay, so if we take this predicate and we apply it to Anna, this will reduce to the sentence, Anna runs quickly and Anna runs gracefully. So we've got this nice kind of equivalence between applying the predicate to an individual and just the straightforward sentence in which we're expressing each of those conjuncts of Anna. There's a more general reason why people working in contemporary formal semantics really love type theory, type lambda calculus, and that is because it meshes in a really nice way with the way people look at syntax, okay? So if we take some sentence, we want to be able to analyze its syntax, and then, as it were, pass that over to the semantics people to analyze its meaning. And the way a lot of people analyze syntax is in terms of what's called categorical grammar. So we're going to take some terms, some words, and we're going to assign them categories, which are going to be like instructions for telling us how to put sentences together in well-formed ways. Let's take the example of a transitive verb, likes. It's going to have this category. And that means it wants a noun phrase, like a name, on its right, and it wants another noun phrase on its left. And if you do that, it's going to give you a sentence. So this is the grammar, the syntax of the term likes. But that's going to correspond really closely to what we said in our type theory, right? Because likes as a meaning is going to be a function that takes in one individual, something corresponding to a noun phrase, and then gives back another function, which again takes in an individual and gives us back a truth value. And a truth value is the kind of thing that corresponds to a sentence. So we have this lovely matching up between the syntax and the semantics when it's done with type theory. So this kind of approach to semantics, formal semantics or compositional semantics, comes from Richard Montague in the 50s, okay? So it's sometimes called Montague grammar. It was really developed by Montague in a couple of papers. He died pretty early, but then it was taken up by people like David Lewis. He introduced it to philosophers, and then it's been developed by a whole bunch of linguists and philosophers, notably by Barbara Party. Finally, let's talk about type theory in philosophy, and I'm going to think particularly here about metaphysics. Now, for a long time, type theory, lambdas, they just had no role to play in philosophy. You know, it started in philosophy with Bertrand Russell, but it was kind of ignored by a lot of people. And in philosophy, you know, I never learnt about this stuff. Pretty much right through the 20th century, you hardly saw a lambda in a philosophy paper. I learned about this stuff by going over to the computer science department, where lots of people use this kind of every day. But in the last, 10, 15 years or so, you've started seeing lambdas cropping up in philosophy papers. I wrote a paper back in, 2011 or 12 about states of affairs that kind of used type theory. Other people have been using it. Kian Dorr had this very influential paper, To Be an F is to Be a G. I think it's from 2013, that basically used type theory to analyze these kind of locutions. And basically there's been an explosion of people using type theory in metaphysics, higher order metaphysics. So higher order metaphysics is the idea of basically using higher order logics, higher order quantification to address traditional metaphysical issues. Okay, so one way we can do that is we can be really clear about the distinction between first order quantification over individuals, second order quantification, which you might think of being over properties, propositional quantification over, you might say, over propositions, but essentially it's allowing us to quantify into sentence position. So what is the philosophical import of this? Well, think about those age-old metaphysical disputes, like over properties. What are properties? Do they really exist? Are they Platonic, located nowhere in space and time, but really existing? Or are they Aristotelian, somehow multi-located in space and time? Or are they kind of just like nominalists say in words or in thought, having no real existence beyond that? Well, the defender of higher order metaphysics might say, all of this way of talking is a mistake, okay? Because to say, where are properties, are they in space or not, is to kind of confuse this kind of quantifier, the quantifier over properties, with this first order quantifier, okay? When we're talking about things being located, we're talking in first order objectual terms. But it doesn't make sense to apply that kind of quantifier to that kind of thing. They are second order things. I'm not sure I agree with that, but that is what the higher order metaphysicians say. Similarly, think about all the debates in philosophy of language about propositions. Like, do propositions exist? What is their nature? Do they exist, even if we didn't have language or thought or whatever? Well, again, higher order metaphysicians can say that's a mistaken way of thinking because it's confusing this kind of quantifier over propositions with this kind of quantifier over objects. It's trying to turn proposition talk into object talk. And at least according to the higher order metaphysicians, propositions aren't objects. In fact, when I said that's a quantifier over propositions, that's probably a bad way of talking because that makes it sound like it's a quantifier over some kind of object. This quantifies over things, but this is doing something else. And then you might say, well, what's it doing? And what defenders of higher order metaphysics tend to say is, well, you have to learn what these things mean by using the logic, okay? Maybe we shouldn't even read this as saying there exists an X. Maybe we should just say something like some X or whatever, okay? It's its own locution that you learn about by learning how to use the logic. Definitely we don't work out the meaning of that by thinking about the meaning of the first order objectual quantifier. Now, I'm not saying this is the right way to think, but it's a way of thinking that has become very, very influential in contemporary metaphysics. Okay, guys, so there you have it. Type theory in computer science, in linguistics, in philosophy, in logic. I said it was going to be a big one, and it was. I've really, really enjoyed putting this together. I think this has been the longest and most in-depth video I've made in a long time. If you would like to see more in-depth content like this, you can buy me a coffee over on Ko-Fi or sign up there as a subscriber. If you've enjoyed watching this, do me a favour, hit that thumbs up, subscribe to the channel, that really helps me out. If you've got any questions about this content, leave me a comment down below. I'm going to try to respond to all of them. Thank you so much to all my Ko-Fi supporters for making this content possible, and to you guys for watching this far. I really appreciate it, and I hope to see you back on Attic Philosophy soon.